Hello everyone. So we're looking at our last section in the theme of chemical kinetics, and that is to look at the microscopic origin, or in other words, the molecular origin of reaction rates. And we're trying to understand, so the whole topic has been on why do reactions, what is the reaction rate and what it is. And this little section is now going to focus on how can we use our molecular understanding of reactions to describe what a reaction rate is dependent on. And you might recall from an earlier part of the section that we said that reaction rates generally depend on the concentration of reactants, the temperature of the reaction system, and then whether or not there's a catalyst present. But what actually is happening at the molecular level? At the molecular level, we need molecules to collide with one another for a reaction to take place. And this links to something called the collision theory of reaction rates. So, for molecules to collide with one another, there are three things that actually need to occur. So, firstly, they must collide, and they need to collide with sufficient energy. In other words, there needs to be enough energy for them to actually bump into each other to break bonds and to form new bonds. And we'll look at what that exactly means. And then lastly, they also need to have the correct orientation. So meaning the correct atoms need to be colliding with each other um, for them to form the correct bonds and to break the correct bonds. If the incorrect atoms are colliding with each other, then the incorrect pathway, or meaning there might be a situation where whatever pathway is happening does not have sufficient energy. So that's what's happening at the molecular level. These molecules are colliding with each other, and whatever that collision is needs to have sufficient energy to have the breaking and formation of bonds. And of course, it needs to be the correct type of collisions, meaning the correct orientation for the reaction that you are considering or looking at. All right. So now, where does all this start to link? So the first thing is that we looked at way at the beginning. We said that a rate is proportional to the concentration of a species, right? And now, inherently, what happens if we increase the concentration? The concentration will be linked to the number of collisions. And why is it linked to the number of collisions? Well, if you think you have a confined space, meaning like a reaction beaker or reaction flask, and if you increase the concentration of your species, literally the number of molecules in that space, then of course the number of collisions per minute or per second or per unit time is going to increase because you physically have more molecules in the same amount of space because you've increased the concentration, and so you will have more collisions. And that inherently increases your rate of your reaction because you satisfy that first condition of the collision theory. There are more collisions, more molecules are able to collide with each other. All right, so that is why we can explain the dependence of reaction rate on concentration, because there's a direct proportionality between the concentration of each reactant to the number of collisions, which inherently increases the rate, because the rate depends on the molecular level at how many collisions there are per time unit. All right. If we move to the second point, meaning reactant molecules must collide with sufficient energy. Now, what does that mean? The energy referred to is something called the activation energy. So meaning literally the minimum amount of energy required to form or to break bonds. So meaning the energy needed for the reaction to proceed. And how we visualize or look at it is like it's an energy barrier. So it's the energy required to cross a barrier, and which is called the activation energy. And you can see it here in this thing called a reaction coordinate diagram. Reaction coordinate diagram. And what we basically do is we monitor the reaction's progress and we look at the energy required. So it says the reaction needs so much energy, or the reactant needs so much energy, right? This is how much energy it needs, and we give it the symbol EA, activation energy. It needs so much energy to absorb so much energy for it to have a successful collision, for it then to form the products. All right, so if you look at this reaction in the forward direction, you notice that the NO2, so the NO2 here and the CO, need to collide in a way that this molecule is orientated. The NO2 has an oxygen orientated with a carbon. And that then forms a very special orientation whereby the bond between, so if we look at the bond between NO, so I mean, remember it's technically there's a resonance structure. I don't really want to draw this now like perfectly correct, but let's do that in any case. So, right, you have your resonance structure here, or your NO2, and you have your C, you have your CO, and this forms what we call a transition state with one another. This oxygen has to be orientated to this carbon over here, because what's going to happen is there is going to be a breakage of a bond between these two. These bonds are going to break between the nitrogen and the oxygen, and there's going to be a formation of a bond between that oxygen and that carbon to form nitrous oxide and carbon dioxide. So you notice the collision needs to have the correct orientation, and it needs to form a bond and break two bonds. And the energy required for that specific setup to happen, we call the activation energy. Okay, so, and that's of course for the forward reaction. So that's what we do. That is how we visualize it and what needs to happen. And of course, depending on your specific reaction, that activation energy is going to be a certain value. Easy, let's call it easy reactions, will have a small value. More difficult reactions, depending on how difficult these orientations are and whatever, this activation energy will be larger or smaller. All right. You might also ask yourself, so right, this reaction that is, as it's written here, is an equilibrium. So it indicates that the reaction can happen in the forward or the reverse. So for the reverse reaction, the activation energy is much lower than what it is for the reverse reaction, because it says if these two products were to collide with one another again, and they collide with one another in the correct orientation, it needs a certain amount of energy, which is 358 kilojoule, then it would be able to form the reactants again. Okay, so that's what activation energy is. It's literally the barrier or the amount of energy required to form the products of a reaction. All right. Right. The only thing I think I need to discuss though is this transition state. And I've already kind of discussed it. The transition state is that specific orientation where just before the bonds break and the bonds form, that the reaction system exists. And unfortunately, it's not a very stable state. As you can see, it's the state with the highest energy in the whole system. And that means it's not stable because it wants to decompose. It wants to break up into the products of whichever way of the reaction that you're looking at. So either in the forward or the reverse direction. So that transition state is not stable. It just is, like it says, it's transitioning from the products to the, or the reactants to the product, and hence you're not able to isolate that state ever in any point. It just represents the maximum potential energy in the system, and it represents the point where our system has sufficient energy and correct orientation to lead to the rearrangement of the atoms to form the product. All right. An analogy that might help is, this is literally like if you have to hit a ball over the net. So like if you have to hit a volleyball over a net, the ball has to travel over that net, and you have to give it enough energy to go over that net and land on the other side. And the energy required to move over that is the activation energy from wherever the ball starts to its highest point. That potential, or that energy you need to get it over, is what we call the activation energy. All right. The next logical thing then to ask is, if we now know how much energy something requires, is there then a way, so meaning we know the reaction needs X amount energy to proceed. So what is the variable that we can change to ensure that we give the reaction enough energy to proceed? And that, of course, is the temperature. So what we look at is how temperature affects the reaction rate. And if you recall the Boltzmann distribution of energy, so the graph here on the right-hand side, you might recall at a higher temperature, your fraction of molecules that have higher energy increases, right? So meaning this red fraction versus the blue fraction is larger. So the red fraction is larger than the blue fraction. And that is because at a higher temperature, the average distribution has shifted to the right in terms of energy. So your average energy per molecule is higher. So meaning literally at a higher temperature, the average energy of all your molecules is physically higher. And that means, in terms of this graph, the percentage of molecules that will be able to go over the barrier will be more. So if more molecules are able to go over the barrier, it means that the reaction will proceed quicker. All right? That kind of makes sense, I hope. So if we increase the temperature, it means more molecules will be able to get over the barrier. It will be easier for them to do so quicker than if we were at a lower temperature, because then a smaller fraction, so meaning like the blue fraction, will be able, then only a small fraction of them have enough energy to get over the barrier. Whereas at the red temperature, a larger fraction of them, or percentage of them, have enough energy to get over the barrier. Okay, so that is why if we increase the temperature of our sample, then we increase the rate. So here, the rate of the reaction can be increased by heating the sample. Raising the temperature increases the rate by increasing the fraction of molecules with enough energy to surmount the activation energy barrier. So it's all about the temperature doesn't lower the activation energy, it just increases the average energy of the molecules. So we give the molecules enough energy to collide with each other to overcome the activation energy. All right, very important distinction. So that is like your coffee in the morning. The temperature is, if at a lower temperature, you don't have coffee in the morning, so hence you're not able to overcome the barrier, and then you do not attend class. If we increase the temperature and hence give you a cup of coffee in the morning, then you have enough activation energy to wake up, get ready, and come to class. And you can hence overcome your activation energy barrier of coming to class. And that's exactly how molecules work. If we, on average, give them more energy by increasing their temperature, they can overcome the activation energy barrier. More of them, the fraction of them that can overcome that at a specific temperature will be higher. Okay. Now, before we move on to that, the last little thing is talking about just the effect of the molecular orientation. Now, that's actually this is just a comment to say that remember that not only must a molecule have sufficient energy to do the collision, or must there be sufficient number of collisions, they must have the correct orientation. So meaning that you cannot have the molecules like the ones that we looked at collide in the way of like this, right? So this collision is not going to satisfy our previous reaction. It has to be in the way of it wants to react like that. That is how it wants to react. Okay, so this orientation is correct. This one will not lead to a product forming. So correct orientation also dictates reaction rate. And the question is, now imagine if you had more than two molecules reacting and all of them have to have the correct orientation. So that then also dictates the fraction of collisions that are correct. So because it's not only the collisions and the activation energy, it's like this fraction of molecules that have to have the correct orientation. And so hence it's actually, amazing that many reactions are so fast as they are. So that's my final point on this. In the next video, we will start looking at, now that we have all this information, all this understanding of the molecular viewpoint of reactions, what can we do with that? How can we calculate anything useful and so forth? Right, so let's quickly revise. What have we learned? So we learned that molecules must collide with one another, they need to have sufficient energy, and they need to have the correct orientation. We then said concentration is, if we increase the concentration, that leads to more collisions. That's it. We then spoke about activation energy and how we can use the temperature to assist us in overcoming the activation energy. And we just basically spoke here about the effect of orientation. So meaning it needs to have the correct orientation. And those are the three factors that govern whether or not a reaction rate what is the reaction rate going to be? Is it going to be high or is it going to be low? All right, so that's your molecular view. So why do reaction rates, are they high or are they low? We will see in the next video a very useful equation called the Arrhenius equation, how that draws all those things together in a good way, and how we can calculate the rate constant and the activation energy. All right, thank you for watching, and I'll see you in the next video.